At the optimizer, we can apply different models of plan optimization. We can use rule-based optimization, where we replace some expressions with others, similar to what we have observed by far with our array laws. This mostly applies to the logical query plans. We can also apply cost model, estimate what is the cost of executing a query plan, and optimize the plan with the goal of reducing that cost. This involves knowledge or assumptions about storage and physical structure. We can also use adaptive plans that update the plan during execution time based on feedback. We will discuss all of these models in our query optimization discussions. However, as we are learning the building blocks before applying, in the next couple of slides, we are going to talk about the basics we will need for the cost model. So, assume we have our logical query plan. The next step towards executing the query, as we discuss in the query processing building blocks, is acquiring the physical query plan. The steps involved in this process include size estimation and cost-based enumeration. In size estimations, we try to come up with a relative size of intermediate steps in the execution of our query. Basically, the question that, what are the size of our intermediate tables? In cost-based enumeration, we decide about order of groupings for associative and commutative operations. Also, on algorithms for each operator in the logical plan. For example, should we use hash join or nested loop join? Why is that important? For example, for this last question about the joins, in a hash join, the database does a full scan of the driving table, builds a RAM hash table, and then probes for matching rows in the other table. For certain types of SQL, the hash join will execute faster than a nested loop join, but the hash join uses more RAM resources. The nested loop join is one of the original table join plans, and it remains the most common. In a nested loop join, we have two tables, a driving table and a secondary table. The rows are usually accessed from the driving table index range scan. And the driving table result set is then nested within a probe of the second table using an index range scan method. You can see the parameters that can affect the choice. These are important and decided in the optimizer and during plan enumeration. We also decide about need of additional operators not explicitly present in the logical plan, as well as on argument passing. In the rest of the session, we will discuss estimating the size of intermediate relations as a preliminary step. We will learn more about cost-based enumeration in our query optimization discussions. Okay, now the size estimation. The size of the blocks and records we are working with in our queries has a huge impact on our query performance. As a part of query compilation, one of the factors to consider is size of intermediate tables. This is considered in physical query planning in order to minimize the estimated cost of evaluating the query. We are going to discuss some basic size parameters. First, B for the relation R, which is the number of blocks needed to hold relation R. Second, T for relation R, which is the number of tuples in the relation R. And last, V of R and A, which is called value count for attribute A of relation R. This value is the number of distinct values relation R has for attribute A. We use these parameters and a few estimation rules to estimate the number of tuples in an intermediate relation involved in our query evaluation.